Hey everyone, this is Dr. Walker. This is video 237, resistors in parallel. I'd like to start off this one with a question. How is this possible? You plug in an electric heater and the fridge turns off. So that, might be a slight exaggeration, but you may have this happen that you have too many things plugged in and then everything or one of the items just go off. This actually used to happen in my old house where if I had the microwave and electric oven on at the same time, then they will go off. So any ideas what is happening there? Please put your thoughts in the comments below. That's going to bring us to this video, resistors in parallel. So this figure shows two resistors in parallel. They're connected at both ends. So you can see that one side of the light bulb, which is a resistor, is connected to one side of the light bulb, and the other end is connected to the other end, and there is a junction in between. Might not be the easiest picture to see. We'll see a better picture in the next slide here, right here. So these are two resistors in parallel. You can see that this end is connected here. There is a junction in between. This end is connected here, and there is a junction between. Another way to think about resistors in parallel is that they are both directly connected to the battery. You can see that the right-hand side of the battery here is connected without anything else in the way, and then the left-hand side is connected. So that means R2 is getting the full voltage, and likewise R1 here on the left and on the right is directly connected to voltage. So it's also getting the full voltage. So that's another way to think about our resistors in parallel. So what we're going to do in this section is simplify our two resistors in parallel into one equivalent resistance that has a resistance of R equivalent. Once again, there are three rules that we need to know for resistors in parallel. The first one is what we just talked about, that the potential difference across each resistor is the same. We can do our numbers again if we have 0 volts for the negative terminal and 9 volts for the positive terminal of our battery. All the points on the left here are at that same potential of 9 volts because there's nothing else there. And then all the points on the right hand side are at 0 volts. So you can see that they all have that delta V of 9 volts across them. And then the next thing is that the current that enters a point or junction must equal the total current leaving that point. So we're talking about points A and B here, which I also call a junction, where we have one or more wires coming together. So if we visualize the current here, I, you can see that when the charges are flowing here, because current is the flow of charges, when they're flowing, then some of them are going to go up and some of them are going to go to the right. So current is going to split up, but you can't have more current than what came in. So whatever comes in must equal what comes out. So in this case, I equals I1 plus I2. And finally, the equivalent resistance is less than any of the individual resistors. So when we simplify this circuit into one that has an R equivalent, then that number that we get for R equivalent using this equation is going to be less than R1 and it's going to be less than R2. And this equation, we can actually derive it very easily if we look at this current equation and we plug in the definition I equals V over R for each current here. Just as a quick exercise, delta V1 over R1 would be I1 here, plus delta V2 over R2. And then that's going to equal delta V over R equivalent. That's going to be the I here. Since all the voltages are the same, then you can disregard the little subscripts. All the voltages are the same. They can cross out to 1. Just cancel them out on each side of the equation. And that's where this equation comes from. The equation that I like to call the 1 over equation. Again, that's just my term for it, but we're going to use the 1 over equation for our resistors that are in parallel. Notice that this is the opposite of what we did for capacitors in parallel. Capacitors in parallel were added, while capacitors in series used the 1/over equation. Let's take a look at one question for this section here. This is a tricky one, so please pause the video and think about this one. It says, when the switch closes, what happens to the battery current? So let's just understand what this means. So when the switch is open, that means that no current can flow through over here. So it's like this part of the circuit doesn't even exist when the switch is open. The current can only flow here through R1. Okay, now let's imagine what happens when the switch is closed. When the switch is closed, that means that it's like we have just a plain wire there instead of the switch, because the charges can't flow through. And now we have two resistors in parallel. So with that in mind, what happens to the current? We have a certain current when it goes through R1. And what happens to that current here now that there is R1 and R2 in parallel? So the best way to do this is to simplify the circuit. When you simplify two resistors in parallel to their equivalent resistance, we just learned that our equivalent is going to be smaller than any of the individual resistors. So we don't even have to do any kind of numbers. We just know that our equivalent is smaller than R1. So now we know everything that we need to know to find a current. I is delta V over R. So they're all getting the same voltage. They're all directly connected to that voltage source. So if the resistance decreased, right, when they were in parallel, we now have less overall resistance because they were in parallel. You can see when the resistance decreases, according to Ohm's law, that means that the current increases. So this one's pretty tricky. Most students always think that the current is going to decrease simply because it looks like we have more resistors. We do have more resistors, but resistors in parallel will actually increase the current because they offer less resistance. So think about that and then enjoy the next video coming right up.